Welcome back to the Deep Dive. Today, our mission really is to sift through some pretty technical research for you. We're looking at something seemingly small cutting tools, but finding out how critical they actually are for manufacturing sustainability. Usually when we talk about sustainability, climate change, it's all electric cars, solar panels, big stuff. But we're going deep into heavy industry. The question is, can a tiny thing like a drill insert genuinely shift the environmental needle in manufacturing?
That's exactly the tension we're digging into. Manufacturing, well, it uses a lot of resources. Think energy consumption, material waste, pollution. It's significant. So if we're serious about hitting environmental goals, adopting sustainable production tech isn't just nice to have, it's essential, a necessary commitment.
Right. And the impact we're measuring often comes down to greenhouse gas emissions, GHG. Now, most people might think, okay, that's about the power plant supplying the factory. But your sources argue the real leverage point is, surprisingly, right there at the machining process itself.
Precisely. Machining is fundamental to how we shape metal. And that cutting action, it takes a huge amount of energy. But here's the interesting part. The tool itself, which might look simple, it's actually engineered quite deliberately to manage how that energy is used. Optimize the tool, you optimize the whole system's efficiency.
Okay, let's unpack that a bit. If a better tool acts like an energy manager, what specific technical things are built into it? What makes it an environmental plus? I'm guessing it involves physics, like minimizing friction and force.
You're spot on, yeah. Imagine trying to push something heavy, a rough floor versus a smooth one. You want less resistance. So with cutting tools, advanced geometries are designed specifically to present the least resistance to the material being cut. This means less cutting force is needed to actually make the chip.
Less force means less power drawn by the machine. Simple as that.
Fundamentally, yes. And then there's vibration. Anyone who's drilled into something tough knows that feeling, that sound. Chatter. It feels inefficient. It is inefficient. That chatter, it translates directly into force oscillation, basically energy just bouncing around wasted. So clever anti-vibration designs, whether in the tool body or the cutting-edge geometry itself, they're crucial. They smooth out the cut, stabilize the force, make the machine use power consistently, efficiently.
Okay, geometry, anti-vibration. What about the actual surface of the tool? You mentioned coatings earlier.
Yes, surface science is absolutely key here. Advanced coatings enhance lubricity. That's just a technical way of saying they make the tool surface more slippery. Reducing friction right at the cutting edge means less heat is generated. And heat, in this context, is just wasted energy going into the workpiece, the tool, the chip, everywhere you don't want it.
So lower friction, stable force.
Yeah.
That cuts energy use. But you still generate some heat. How do you manage that?
That's the final piece for this part of the puzzle, yeah. Efficient cooling. Even with low friction, you get heat, so you need effective ways to remove it. Sometimes that means high-pressure coolant, aimed exactly at the cutting zone. So you look at these four things together: geometry, vibration control, coatings, cooling. Collectively, they make a substantial difference. They really do reduce the overall environmental footprint of that machining operation.
That's quite a lot of engineering packed into such a small component.
Yeah.
Okay, let's shift gears slightly. Performance and sustainability. Historically, manufacturers often saw a trade-off, right? Faster speeds meant you chewed through tools faster. But the sources suggest this is changing. That speed is now sustainable. How?
It's a bit of a conceptual shift, yeah. We used to see productivity purely in dollars and cents. Now we need to see it as an environmental metric too. Think about it. Reliable, high productivity tools mean you spend less time cutting each part.
Less cutting time.
Means less machine power consumed per part, and therefore lower GHG emissions tied to that energy use. It's a direct link.
Okay, I get the time-saving part, but I'm still a bit skeptical on tool life. If you run faster, surely the tool wears out quicker. More tool replacements, more waste from the tools themselves.
That's where the modern engineering comes in. The goal now is higher speeds without that traditional sacrifice in durability. Good engineering achieves both. And when tools genuinely last longer, you replace them less often. You index inserts less frequently.
Which cuts down on machine downtime.
Oh.
Okay, because when the machine stopped for a tool change, it's still powered up, maybe idling, wasting energy.
Exactly. Every minute that machine is running but not actually cutting metal, it's consuming standby power, maybe power for movements that aren't productive. So reducing that downtime for tool changes significantly boosts the overall system efficiency. Less idle time equals less waste. Simple.
Now this is where it gets really interesting, especially for anyone managing a shop floor. The sources talk about a dual effect, where the tool's quality actually eliminates whole steps in the manufacturing process.
This is a huge win for sustainability, and honestly, often overlooked. If your cutting tool delivers an outstanding surface finish on the part, you might not need those subsequent finishing operations like grinding or polishing. Think of the time, the energy, the extra machines you don't need to run.
So the tool is so effective, it streamlines the whole production chain. Wow. But you also mentioned it affects material waste right at the beginning.
Yes, because if you know you don't need a separate finishing step, you don't need to leave as much extra material in the part initially. You reduce the machining allowance, the stock that needs to be removed. Less stock removal means you start with less raw material in the first place.
Ah, okay. So that's the dual benefit. Less machining time and less material waste from the original blocker bar.
Precisely. It's a double win.
That's genuinely impressive. Okay, we've established the why. Why better performance equals better sustainability. But how does this actually work on a busy shop floor where seconds count?
We need to look at efficiency and handling the tools themselves. Right. And that brings us to innovation in tool design, specifically modularity. If tools have complex parts and some wear out faster than others, the smart, sustainable approach is to only replace the worn-out bit. This is the idea behind systems with exchangeable cutting heads, usually made of cemented carbide.
Like those case studies you mentioned. ISCAR's tools, Multimaster and SumoCam.
Correct. Systems like Multimaster allow for a much more rational use of that valuable cutting material, the carbide. You're just swapping out a small, worn head, not discarding the entire steel tool body. That's significant material sustainability right there.
And this modular approach, this leads to what you call the ultimate efficiency aha moment. The end setup time principle.
Absolutely. It's a game changer. Because these systems are engineered for incredibly high repeatability, when you swap a worn head for a new one, it seats perfectly. You don't need those extra setup steps like bringing in a probe to touch off the tool or fiddling with machine offsets to compensate for tiny errors.
Eliminating that setup time, that directly slashes machine downtime again. Boosts efficiency, boosts sustainability.
Exactly. Less downtime, more parts made per hour, less energy wasted.
Let's put some numbers on this. There's a specific data nugget in the source about Logic 3 cam drilling system. The big change there was going from the usual 2 flutes, or cutting edges, to 3. Seems simple, but what did it do?
It's simple geometry, yes, but used very strategically. Adding that third flute allows the tool to handle higher feed rates and speeds safely. We're talking increases of up to 50%. It's a major jump in potential productivity for drilling operations.
Okay, faster is good, but the sustainability proof is in the energy numbers, right?
Uh-huh.
There's a specific test case. Drilling 16-millimeter holes, pretty deep, 80 millimeters in low alloy steel. What did that comparison show?
Right, so they compared this new 3-flute system against a competitor's standard 2-flute head. They kept the tool life consistent, let's say 500 holes for both. The results were quite striking. The 3-flute system delivered a 26% decrease in cycle time.
Wow, over a quarter less time to drill the same hole. That's huge for throughput on a production line.
And here's the direct environmental link. That faster cycle time translated directly into a 19% decrease in energy consumption for that operation.
19% less energy.
And because energy use and CO2 emissions are directly linked in most manufacturing contexts, that also means CO2 emissions were reduced by 19%, a direct consequence.
Hang on, let's pause on that 19%.
Yeah.
If you're a big manufacturer running thousands, maybe tens of thousands of these drilling ops a day, a 19% energy and CO2 reduction from just changing the drill head design. That moves from being, a neat technical detail to a major factor in cost savings and meeting environmental regulations. That's bottom line impact from a tiny piece of metal geometry.
Exactly right. It clearly demonstrates that better performance is better for the environment. It's not a trade-off anymore, it's synergistic.
Okay, so beyond just adding flutes, let's look at some other advanced techniques. What other geometric tricks are designers using now to fight vibration and make tools last longer, especially in more complex cutting?
Well, besides things like dedicated anti-vibration mechanisms often built into long, boring bars, the design of solid tools, like end mills, is getting really sophisticated. They're incorporating chatter-resistant cutting geometries. Common techniques include using a variable helix and an unequal angular pitch on the flutes.
Okay, jargon alert. Let's break that down. Variable helix, unequal pitch.
Yeah.
What does that actually do? Why does it help?
Okay, think of it like noise cancellation, but for physical vibrations. A standard tool has evenly spaced flutes with a constant twist angle, the helix. This can set up a harmonic resonance, like hitting the same note over and over. That's chatter. By varying the twist angle along the flute, the variable helix, and changing the spacing between the cutting edges, the unequal pitch, you break up that regular pattern.
So it disrupts the rhythm of the impacts, prevents that resonance from building up.
Exactly. It's a kind of built-in mechanical damping. It passively resists chatter, which means the tool lasts longer, cuts smoother, and gives you a bigger surface finish.
Makes sense. What about getting more life out of the tools people already have? Any tricks there for material sustainability?
Yes. There's a clever idea called the Smart Pocket Reducer. This is basically an adapter. It lets manufacturers fit smaller-sized inserts into existing tool bodies that were designed for larger ones.
So you don't have to throw away a perfectly good, larger tool holder just because you want to use a slightly smaller, perhaps more efficient or specialized insert.
Precisely. It extends the usable life of the tool body itself. That reduces waste, both the steel of the body and the energy, the GHG emissions, needed to make a new one. It's about maximizing the value of what you already own.
Very practical. Okay, finally, let's touch on the really cutting-edge stuff. Additive manufacturing, or AM, essentially 3D printing. How is that being used in tool design for sustainability?
AM, or 3D printing, offers at least two really significant sustainability advantages for tool making. The first one is all about material efficiency. AM lets you build a tool body very close to its final shape right from the start. We call this near-net shape manufacturing.
Meaning much less material needs to be machined away afterwards to get the final tool. Less waste from the get-go.
Exactly. You minimize that finished machining. It drastically reduces the amount of expensive tool material, often special steels, that gets consumed just to create the body. You're building up only what's needed instead of cutting down from a big block.
Okay, less material waste.
Right.
What's the second advantage? You mentioned cooling earlier.
Yes, and this is potentially transformative for performance and sustainability. AM makes it much, much easier to create optimized internal coolant channels within the tool body. Traditional methods like drilling usually limit you to straight channels, but with AM you can design complex, curved, almost organic-looking channels.
Why would you want curved channels?
Because heat doesn't always build up conveniently near a straight line. AM allows designers to route those coolant channels precisely to follow the areas where the most heat is generated during cutting. This means you can deliver coolant much more effectively right to the hottest spots in the cutting zone. Better cooling efficiency means longer tool life, better part quality, and again, less wasted energy manifested as heat.
So wrapping this all up, we started asking if a tiny cutting tool could really make a difference to global manufacturing's environmental impact. Where have we landed?
I think the conclusion is a clear yes. The idea of a sustainable cutting tool isn't just marketing fluff. It's a real concept, deeply woven into modern manufacturing thinking now. Through smart design, minimizing friction, using materials wisely with modularity and AM, using geometry to boost efficiency. These advanced tools lead to real cost savings, measurable reductions in waste, and genuine environmental benefits.
It definitely feels like it introduces a new dynamic, or maybe a new tension, in how tools are developed and chosen. For years, it was all about performance, right? Raw speed, how long the tool lasted, that was king. But now, this sustainability aspect, backed by actual energy data, seems to be becoming just as important. It's driving innovation in a new direction.
Absolutely. The future of cutting tool technology really lies at that intersection where efficiency meets ecology.
Which brings us to our final thought, something for you, the listener, to chew on. Given that a tool's performance, how fast it cuts, how well it finishes a part, seems increasingly tied directly to its environmental footprint, its GHG emissions.
Sure.
What should modern manufacturers be prioritizing right now on their procurement checklists? Is it still just about the raw speed and the guaranteed tool life? Or should they be demanding verifiable data from suppliers on energy consumption per part produced? Where should the focus be?